This November is the 10-year anniversary of this Mark Rober video, which has gathered over 30 million views in the last 10 years on the best strategy in the kids game Guess Who. Now, Mark argues in this video that instead of doing the typical guesses, like is your character wearing a hat, does your character have red hair, it is better to do guesses that have a wider pool of people for whom the answer is yes. In fact, he says the best thing to do is to cleanly divide the population in two, where half the people are a yes answer and half the people are a no answer. Now, this is sometimes called binary search in computer science, and Mark says this is the best Guess Who strategy. Now, in 2024, he released an updated video, a short video, with the same kind of idea, and he calls this one How to Always Win in Guess Who. This one has received an astounding 126 million views, which I think is more than any math video anywhere on YouTube. Now, Mark is an absolute genius on taking these ideas from math and science and making them accessible to everybody and showing them off in interesting ways. But in this case, Mark has missed an interesting mathematical idea that I want to tell you about. And the reason I know about this is because it's also the 10-year anniversary of my paper on the optimal strategy in Guess Who, which I put on the archive 2 months before Mark made his video, also 10 years ago. Now, in the final version, which was published in 2016, a year later, I made sure to include the subtitle Beyond Binary Search, because the optimal strategy is not to always do a clean division by 2. There are some situations where you do want to make these extreme guesses, and that is what my paper is about, and it proves the optimal strategy using mathematical formulas. Now, to celebrate the big 10-year anniversary of my proof, I've made a web app where you can play the game Guess Who against a computer program that is running this optimal strategy, so you can get a first-hand experience of what this strategy is like. You can also stick around because I recorded a 25-minute presentation I recently gave at some Math Club lightning talks where I talk all about my paper and the journey I went through and how I discovered it and why I think it's a good story of sort of the luck involved in math research and where these ideas come from in real life.
So I have a screenshot here. This is the first page of my paper on the optimal strategy in Guess Who, which I wrote when I was a PhD student. And this was one of my first papers that I did all on my own. And here is the little abstract. Guess Who is a popular 2-player game where players ask yes or no questions. This is my son's version of Guess Who that I brought in for show and tell today. In his version, you can slide out the thing. So this one has pets. There's different pets. This is different foods. And you ask yes or no questions. So you might ask a question like, is your secret food, is it a vegetable? And if the answer is no, then you would knock down all the vegetables. And then you would say, does your thing have chocolate on it? And then you would knock down all the ones that have chocolate on it. Who's played Guess Who before? Yes, almost everybody. That's very good. And the thing you might ask mathematically is, what are the best questions to ask? Do you want to ask a question that there's only a few answers yes to, or do you want to like split it up and kind of split it 50-50? And what I wrote here in this abstract, contrary to popular belief, and I believe there's a YouTube video by Mark Rober that has millions of views that says that binary search is the best thing. But in my paper, I prove that performing binary search is not always optimal. So sometimes you don't want to do just a 50-50 split. Instead, the optimal strategy for the player who trails whoever is losing is to make certain bold plays in an attempt to catch up. So if you're losing, you have to take risks to try to catch up. This is discovered by first analyzing a continuous version of the game where players play indefinitely and the winner is never decided after finitely many rounds. So there's some kind of infinite game, some kind of continuity. If you've taken calculus, you'll appreciate that you can sometimes get information about something that is finite by doing the infinite version. And that's what we're going to do here today. Let me first start by saying what the assumptions are and the rules. And to really get things going, I'm going to have us play a round of Guess Who. So I'll have a volunteer who will come up and we'll play a round of Guess Who. Let me tell you the rules first, so you make sure you pay attention to the rules so you cannot be chosen as the volunteer. Here are the rules. So the first rule is that all the characters are equally likely to be drawn as the secret character. You don't get to pick. They are all equally likely at random. And I brought in my 20-sided dice. We're going to play a 20-character pool of Guess Who. We're each going to roll our 20-sided dice to decide who our secret character is. Instead of doing, vegetables or food or pets like I have over here, we're going to do the numbers 1 to 20 because we're boring mathematicians, I guess. Okay, so those will be our secret characters. All right, here is an important thing. You immediately win the game when you reduce to one remaining candidate. So if there's 2 people left and you say, is it this one? And the answer is yes, you immediately win the game. In some versions of Guess Who, there is an extra special rule that says, even after you've determined that it is broccoli, the secret character is broccoli, you have to make a special guess that says, I am accusing you of being broccoli. And only then you win. We're not doing that. We're doing it the math way, which is as soon as you're down to one candidate,
you win the game. I like this version because it's the sudden death mode. You can always win in one turn if you're lucky. You just say, "Are you this guy?" If the answer is yes, you win. Okay, so it's very important. Some people will get mad at me because I'm doing it this way. That's just the way it is. That's what we're doing. Okay, here's another important rule for the mathematical version of Guess Who. You could ask any subset of people you want. So normally when you play with this one, you have to say something like, "Is it a vegetable? Does it have chocolate?" But we're going to be mathematicians, and we're going to say you can do any subset. So you could say, "Is it that one or 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 that one?" That's a valid question. And the answer is either yes or no. It's one of those. But you can create any question you want about any subset. And then the thing that matters is only the size of the subset you're doing, not the details of what you can possibly do or not. So that, again, makes it more mathematical. We're going to use this terminology that when you ask a question where there's B things that correspond to the yes answer, we're going to call that a bid of size D. And this is just to avoid, make a nice short word for this thing that's going to come up a lot. So for example, if I said, if there's five things here on the top row, and I ask a question where the answer is 5, the answer is yes for those 5 things, that would be a bid of size 5 or a size 5 bid. And those are the only rules that you need to know if you've played Guess Who before. And the mathematical question, again, that we want to answer is, what is the optimal bid size? How should we create our questions to maximize our chance of winning the game? What kinds of bids help us win or not? And I'm going to show you kind of the answer to the mathematical question, the optimal strategy in action against a volunteer. So do I have a volunteer who would like to play Guess Who against me? And I will, in addition, so you're not scared, I will also let you go first. So here's my little board that I've set up for us to play Guess Who. And I've done a little calculation. If you go first, you should win 63% of the time. So if you follow the optimal strategy, you'll win 63% of the time. And going first, the optimal strategy is pretty easy. You could probably figure it out. So yeah, do I have any volunteers for who would like to play Guess Who? Yeah, please come on up. Okay. So here's what I'm going to do. I'm going to give you this 20-sided dice. You're going to roll it. And that'll be your secret character. Okay, that's what I'm trying to guess. I'm going to roll this 20-sided dice. That's what you're trying to guess. I'll show them now where you're under here, so I'm not cheating, okay? Nobody else will know. Okay, so that's my numbers. Okay. All right, and then we're gonna you can stay over there. I will cross things off for you as we go. And we're starting here, so I made a little grid. This is 20 by 20, so this sort of represents the possible states we could be in. And we're starting up here in 20 by 20. So this is where we are on turn 1. There's 20 possibilities for me and 20 possibilities for you. Let's put mine down here. This is me. This is you up here. And you get to go first, so you can ask me any question. I have one of these numbers, 1 to 20. And what question would you like to ask me about my secret number?
Is your number greater than 18?
Greater than 18. Is my number greater than 18? And the answer is no. No, it's not. It is not greater than 18. And that means you can cross off, my number is not 19 or 20. So you can cross these off. And we move. Look, we were in the state where we both had 20. Now you only have 18 numbers left. I still have 20. So we are now in this state. So after turn 2, we are here after turn 2. Because you have 18 left and I have 20 left still. All right, I'm going to ask you a question now. You have thrown a wrench in my plans slightly. Let me see what I want to do. I think I now have, okay, yes. Is your number less than or equal to 10? No. Okay. So the question one was, is it less than or equal to 10? Less than or equal to 10. And the answer is no. And so I can cross off all these numbers. It is not 11, 12, 13, 14. Wait, you said no. Hold on. I got it backwards. All right. You said is it less than or equal to 10? You said no. Okay. It's not these ones. It's one of those ones. 11, 20. Okay. So now we moved all the way to this situation. We are in 10, 18 over here. Like that. So we've gone all the way down here. I've reduced from having 20 candidates. Now I'm down to just 10. 11 to 20. There's 10 possibilities for me. Is that your guess? What would you like to ask me about my number?
Is it a single digit or?
Is it a single digit? That's a great question. Okay. Is it a single digit? A single digit. And my answer is yes, it is a single digit. And that means you can cross off 10, 11, 12, 13, 14, 15, 16, 17, and 18. You are down to 9 possibilities. So the game proceeds all the way over to here to 9, 10. All right. So here we are after turn 4. We are getting close to the end zone over here where there are 9 possibilities for you, but there's still 10 possibilities for me. And now I will ask a question. Is your number less than or equal to 15?
Yes.
Yes. Okay. Is it less than or equal to 15? And the answer was yes. So I can cross out these numbers. And now I am going to move again down to 5 candidates over here. 5 candidates over there. Okay. So we're at 9, 5 on the 5th turn of the game. It is your guess now. What would you like to do? Is it a prime number? No, it's not a prime number. That's a fun guess. Is it prime? Is it prime? And I said no. And so now we can cross out all the prime numbers. So the prime numbers are 2, 3, 5, and 7. Oh, this is I'm going to do it that way, and let's not get into a debate about 1. Okay. Well, what's left? 1, 2, 3, 4, 5. There are 5 left. So we're here. 6. Ooh. Okay. Now I'll ask a question. Is your number less than or equal to 13? Is your number less than or equal to 13? No. Okay, so I'm going to cross out 11, 12, 13. And now I have moved really close to the end zone. I only have 2 possibilities left for me. I'm here in question 7 with 2 possibilities. This is the thing you need to be aware. Next turn, I will surely win the game. Because I will ask you, is it 14? You say yes, and I win. If you say no, then I also win. So I'm going to win the game next round. This is your last chance to snatch victory from me. Please go ahead with your question. Is it number 9? Is my number 9? No. Is it 9? No.
Shit.
No. So unfortunately, my number was 4. Is yours equal to 15? No. Okay, then your number must be 14. Is that correct? Is your number 14? All right, good. Mihai from the future here with a quick little interruption. If you want to also play the game Guess Who against me, you can do that by using this little web app where I have programmed the rules I was using for the optimal strategy into a computer player that will always play this optimal strategy. And it is set up to be exactly the same as the presentation I just gave. And you can drag this little slider around to make different guesses. Unfortunately, I can't let you do things like guess, is it a prime number? You always have to make a guess, is your number between something and something else? A good example would be you might ask, is your number between 11 and 20 inclusive? If you hit make this guess, you will see we have reduced the possibilities down to 10 possibilities. And the computer has also made a guess. They've said, is your number between 1 and 8 inclusive? And in this case, they got lucky, even though they picked a smaller pool than half the remaining candidates. They got lucky, and they're down to 8 candidates. So they got a little bit ahead of us by doing this. So if you want to give that a try, please go ahead to that web app, link in the description. And there's even a little bonus here. If you press the grid button, it'll show you the grid just like from the presentation. All right, good. So that's how a typical game would go. I think you saw some of the strategies that in play here. Can anyone guess what is if you're sort of winning the game, what is the strategy that I was using when I was sort of ahead? Yeah.
Just binary search.
Binary search. So binary search means cut all the possibilities in half. And that is what you do when you are winning the game. It turns out I was winning the game for most of the situation here, so I was able to do binary search a lot, and that's because your first guess went very badly. And after the first time, so I was winning the game after the first round. Okay, well, we're gonna get to this in a second. There is one other strategy that sort of came up near the end that you saw. What happens when you start to lose the game? Do you still do binary search, or do you start to do something else? What happens when you're losing the game? Gamble. Yes, that's right. So you saw that right at the end, right? I was about to win, and right at the end, I was about to win. The best that you can do is take a gamble. And this is the other part of the strategy. Half the time you do binary search. That's if you're winning. That's like the safe play. You play no risk. You do binary search. And then when you are losing the game, then you want to take these big gambles. And the gambles get more and more extreme the more you're losing. And that's what we're going to learn. So I'm going to tell you the story. I'm going to tell you what the final answer is, but I'm going to structure this instead of just telling you here's the formula. I'm going to structure this as a little bit of a story, not of what the formula is, but how did I discover the formula? Okay. And this is what I call a story of mathematical serendipity. What is serendipity? I went to the Wikipedia page for serendipitous inventions. Post-it notes were invented by accident. They were kind of trying to make glue, and their glue was too bad. And then they're like, oh, wait, this is actually kind of useful as a Post-it note. Velcro, they were trying to do something else. And they're like, oh, wait, this is actually very useful for this. Silly putty, that's actually very useful for something else. And the same thing in the optimal strategy, you guess who, which I have photoshopped in here. There's some weird step in this sequence of things where there's like a bolt of lightning from the blue, and then we get the formula. You'll see what I mean. Okay, so what is step one? Step one, this is the non-interesting step. This is the kind of thing you could do in a class on probability, is to make a recursion relationship for the strategies of what's going to happen. So when player one has n people and player two has n people, and it is player one's turn, something happens, and you can know the exact probabilities for those things. And the things that will happen is if I make a bid of size B, then I will either have B people act or I will have n minus B people act. So when going back to our little game over here, when I was, for example, when I said I had 20 people out, I said, is it less than 10? I was either in it down to 10 or I was sending it down to 20 minus 10. So those are two things that could happen, and they were equally likely. In the very first guess of the game, when you said, is it less than or equal to 18? There was an 18 out of 20 chance you would end up with 18 people left, and there's a 2 out of 20 chance you would end up with two people left. So whenever you make a bid, because it's a dice roll and everything is equally likely, the size of your bid controls the probabilities of what will happen next. So this is the basic fact that you could do in a first-year probability class. When you select B people and you ask, is the dice roll one of these B people, the probability is B over N. When you're doing conditioning, the information you have, the property will continue. So this is a nice probability fact. And this means that you can come up with a recurrence relationship for the optimal win probability. This is what I call P star. And this is if you played perfectly as well as you could, what is the chance you would win when I had n players left and you have m players left. And the optimal bit size D star, which is the optimal size for me to make my guess. Okay. And here is a proposition screenshotted directly from the paper that says what's going on. Of course, we have these probabilities, and P star is the optimal. Well, P star should be the maximum, right? We should take the maximum of all the things that would happen to us, and we can calculate what would happen by using those probabilities. So we get this nice recursion relationship, which looks a little bit funny. It says P star of NN, it's the maximum of something, P star of MP. The M and the N got switched. And that is because when you take a turn in Guess Who, it switches whose turn it is. So NN is on my turn. I have N people and M people. But from your point of view, you have M people to N people. And that's why things get switched over here. And these are B over N and N minus B over N. Those are the two probabilities with the things happening. So this is the kind of recursion relationship that you can get. This is, so far, ho-hum, nothing super special here. The exciting thing is that we're going to be able to somehow solve this very nasty looking equation. If you can just look at it and find the solution, then you'll have the answer to the question. The B star is where does the maximum occur? And that's called the argmax, Okay, that's step one. Okay, what is step two? Well, you take step one, you put it in your big computer, and you say, Mr. Computer, please solve some of these probabilities for me, and we're going to stare at the output until we get some inspiration. So you put this in the computer, and you get a nice graph that looks like this. This is the exact graph we were looking at before when we played the game. It's got N on the x-axis here, which is the number of players that are remaining. In our game, we started at 20, and we worked our way down. This graph goes all the way up to 31. And what I'm plotting here is the optimal bid size. So the computer solved that recurrence relationship for some small values. I only went up to like size 100, and I'm plotting here the first 31. And the optimal bid size is plotted over here in this wide array of 15 colors. And step two is to stare at this output and see if we can find a pattern. So we look at it and say, are there any patterns going on here? Can anyone see a pattern in the outputs? Who's got an idea? Yeah, Gabe.
Those bands look vaguely related to bars of 2.
Yes, that's very good. So this is a band of height 1. In this band, we have many people, and the opponent only has 2 people left. This is exactly what happened at the end. The opponent is going to win next turn, so we got to go for, is your number the number 9, and hope for the best, right? That's this band. But then this band over here is a band of size 2, and in this one, we're bidding for 2 people. So we're not so desperate that we're guessing, hey, is yours the number 9? But it's pretty desperate. We're saying, is it the number 9 or the number 10? So we're trying to get down to 2 people, and we're hoping that we're going to win. And that's because the enemy is surely going to win. They have 3 or 4 people left. They're going to win in 2 turns.
So when they have 2 people left, they're going to win in 1 turn. When they have 3 or 4, they're going to win in 2 turns. We need to stop them by getting down to 2 ourselves. And then this is a band of size 4 over here, where it's height 4, and we're betting 4 people. We're bidding 4 people. So we're saying, is it one of these 4 numbers? And then this is a band of size 8. So there's 8 rows over here where we're bidding 8 people. And this is a nice pattern that continues. And as much as you check on the computer, it will always hold. This is what I call being in the weeds. In these situations, we are losing. And in those losing situations, we need to take these gambles. There's another nice pattern that's a little nice to see on the top here. That's a little easier to describe. There are bands of size 2, and they're always half your current amount. So this is the I'm winning situation up here. This is the I'm losing situation. And in the I'm winning situation, it's always half of what you have rounded down. So if you have 30 or 31 people, you bid 15. If you have 28 or 29 people, you bid 14, and so on. So that's why they're little pockets of size 2. It's half rounded down. And I called these things, I gave them names. So I called the regions U0, U1, U2, U3, W0, W1, W2, W3. And I just saw them just by looking at the output. And this U stands for the upper hand. So when you have the upper hand, you're sort of winning the game, and you can do the safe play of bidding half your current value. So doing a safe play that takes you down by a factor of 2. You'll notice I don't want to say you're winning when you have the upper hand, because there's some situations where you have the upper hand even though you technically have more people than the opponent. So you'll notice this like U2 region, it crosses the diagonal line where you have the same number of people. So I have 15 people and you only have 9 people. I still have the upper hand because it's my turn. And so that extra turn advantage gives me some advantage over here. That's why I call it the upper hand and not just I'm winning. In contrast to this is the W's. The W's stand for in the weeds, in the weeds. You're in the weeds. That means you have to take these gambles to try to catch up. And when you are in the weeds, your optimal bid is always a power of 2. So we saw it was 1, 2, 4, 8. Which power of 2 is it? It's the largest power of 2 less than your opponent's total. So if your opponent has 11 people, you would bid 8. If your opponent has 19 people, you would bid 16, and so on. So you're bidding based on how close your opponent is, not based on what you have. And so what you're trying to do is you make a desperate play to sneak just barely ahead of your opponent on a power of 2. As a formula, this is 2 to the floor of the log 2 of m minus 1. So the largest power of 2 less than what your opponent has. Okay, this is very nice. We've done step 1, write down the recurrence relationship. We've done step 2, we have a guess of what is going on. And now we're going to need some luck. And the first bit of luck happens by doing like what I said, of treating it like a calculus problem. And in calculus class, you don't often deal with n's and m's, with integer numbers. You deal with continuous days. And so I make this approximation of something I call p star infinity, that is like thinking of n and m as being so large that they might as well not even be integers anymore. So I'm going to pretend what would happen if n and m, the number of people we have left, 20 and 20 in the example I did, what if that was not a natural number, but it could be any real number? What if I had 13.7 people left? What would happen in that situation? And then I made up this game called Continuous Guess Who that follows the same kinds of rules as Guess Who, but it's continuous, and we can sort of do calculus and limits and that kind of thing. Actually, I will say, in the very first version of the paper that I submitted to the referee, it wasn't phrased in terms of continuous Guess Who. It was phrased in terms of very large n and m values. So I said as n and m get really large, then you have these approximations. And then the referee was like, this doesn't really make any sense. Are you trying to say things are continuous? And I was like, yes, so that's exactly what I'm doing. So now in the version 2, in the published version, there's a nice acknowledgement to the referee for thanking them of improving my presentation, and everything is explained in terms of continuous Guess Who. I won't go into the super lot of details about what continuous Guess Who is, but you should just think of generalizing it. Instead of being n and m being integers, they can be any real number. And when you have any real number, the game can go on forever. You see, the game does not end when you get down to 1. You can go down to a half, and then a quarter, and then an eighth. And the game can go all the way down. You can have 0.000001 people left, and the game will continue on forever. But the nice thing is you can do calculations like this one for lemma 3.6, which I've screenshotted from the paper, which says that when you are playing continuous Guess Who, if you follow the strategies that were suggested to us by the computer, then if you are in the weeds, I can calculate the probability that you will ever escape the weeds. So if you have 2 to the k times alpha people left, then the probability you ever escape the weeds at any point is 2 over alpha. So in other words, when you are making these desperate plays to try to catch up ahead of your opponent,
your plays get more and more desperate. So you try a desperate play, it doesn't work. You try to even more desperate play, it doesn't work. And you try to even more desperate play, and the total probability you ever get something out of it is some finite amount. It's 2 over alpha, and I can calculate it. I won't give the full details, so I'll skip a lot, but it does end up being a very nice infinite sum. And because continuous guess who is an infinite game that goes on forever, it's an infinite sum, and I can calculate what it is. In this case, it's a geometric sum, and that's very nice. If it was a finite game, that should be a finite sum, and that's much uglier than an infinite sum, it turns out. So infinite sums are nicer in some cases than finite sums. Okay, so that is step 3. We do these kinds of calculations. There's some stuff I'm skipping. This part, I think, was the exciting part where I was like, oh, can I actually work this out? Will it work? And I got some nice formulas. So this was like a little bit of luck that this worked out. But I had this approximation, and in the approximation, I could calculate things. Okay, step 4. Actually, I think I'm going to show you the solution from step 3. You get these nice formulas at the end of the day, depending on if you're in the weeds or if you have the upper hand, and you have these continuous curves that tell you the probability of winning, depending on the ratio of player 1's to player 2's totals. And they're these 2 periodic things. So if x equals 2 to the k times alpha and y equals 2 to the k times beta, you have this L-shaped piece that is going on. And then there'll be another L-shaped piece for 2 to the k plus 1 times alpha and 2 to the k plus 1 times beta that will sort of nestle into that. And together, these L-shaped pieces tile the entire plane. So we're able to calculate things very nicely. But here's where things get exciting. Step 4, let's take our approximation and compare it to the original thing and see how close were we. Were we pretty close? And this is where the magic happens. So I remember typing this on my computer, and I had the difference between my approximation and the true answer, because remember, the computer calculated the true answer. I worked really hard on pen and paper to find the approximate answer. I typed that into the computer, and then I was making graphs of what is this difference? What does it look like? And I remember vividly when I multiplied this difference by n times n, the graphs became constant. So if you take this difference, you put it in the computer, you're like, how was I close? Did I get a close approximation? It turns out that the difference is exactly -2/3 over nm or 4/3 over nm. And I have no explanation of why this is the way it is. This is an absolute miracle of a formula. The fact that this works out to a nice thing that you can guess is totally unexpected to me. I was expecting it's some number that goes down to 0, but is some crazy, it's got some maybe very complicated formula in NNM, and it's getting closer and closer to 0. Maybe we can hope, if we're really lucky, say how small it is. But the fact that we can get an actual formula is the closest thing I know to a mathematical miracle. We have an actual formula for the difference. And here's why this is so good. You might think, okay, who cares? Like, it's whatever. You have a nice formula for how close you were. Great. But here's the miracle. If you know the difference between 2 numbers, and you know the one number, you actually know both numbers. There's a nice formula. P star is whatever the approximation is plus the difference, you see? So if it turns out that the difference is some easy formula, you take that difference, you tack it on to the thing you had before, and now you have the exact answer, okay? So if you have a nice formula, and you have a nice formula for the difference, now you have the exact formula. And to this day, I do not know why this works. This is like an honest miracle to me. I really could not tell you why this works. This brings us to step 5. Which is the worst of all the steps. A horrendous proof by induction that the formula works. So in all these steps so far, we've guessed the formula P star by looking at the computer output, and it seems like it's this. And now that we have a guess for the formula P star, now we get cracking and we do what I call a horrendous proof by induction. I won't bore you with the details. I will just animate the pages of many lines of big expansions and proof and cases. There's case 1, case 2, case 3. I think there's 3 cases and 2 lemmas. Of some craziness to prove that this thing really does work. But at the end of the day, it really does work. And that's a proof. That's a good enough proof. So to summarize, here is the whole story from sort of start to finish. The sort of obvious thing that probably people have done in the past is to get this recursive formula for P star and D star. That's not so hard, basic probability. The looking at the computer and then finding the outer hand and in the weeds. The fact that there is a nice pattern that you can see, that's already some kind of good luck. But you guys saw that pattern already. Step 3 is to find an approximation. So I think these are where the skills of being a mathematician, of taking a lot of calculus classes, that's where this paid off, is in step 3 of knowing how to deal with limits and continuous things and infinite sums. That's where I use those in step 3. Step 4, we compare the approximation we got in step 3 to the answer from step 2 that the computer gave us. And this is where the real miracle happens. P star minus P star infinity happens to be a simple formula that we can guess. And then we get
actual good formula for P star. And then we prove that by induction. Just for the record, here is the actual formula for the actual optimal bidding and the actual optimal P stars. And they're very similar to what you saw before in the continuous case, except they have these extra factors of +2 and +1 that are not there. So those tell you the actual best strategy that you can do. Okay, and I think I will stop there. I have a QR code here. I might make a longer version of this at some point. So if there's something I skipped over, please let me know in the QR code. But otherwise, I'm happy to take questions. Thank you so much for listening.
If you're still here, I hope you enjoyed that presentation. And if you want to know more of the mathematical details of how exactly the proofs work and exactly how the equations happen, I highly, highly encourage you to go read my actual paper, which is freely available on the archive, where a lot of mathematical research is posted nowadays. Of all my math papers, this is by far the most readable one. It's in the archive before. Maybe this could be your first one. I think it's a nice paper to start with. It's got some nice pictures and has some nice intuition, and you get these nice little calculations that lead us to the final answer at the end.